Hello everyone. Welcome to the first live section of this NPTEL course, which is Quantum Transport. So, I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm the TA for this course. So, in each live session, what we will do, we'll go through in the first part, we'll go through the concept that has been covered during this week. We'll go through some of the fundamental details and as well as some of the numerical details. After that, after covering the weekly content, we'll also solve few numerical problems that is related to the concept of this week. Okay. So before starting the session, let me know whether my screen as well as whether my voice is audible to you. If not, let me know. You are free to ask me any query or if you have any doubt in the chat box, or please let me know if you want me to unmute yourself. So feel free to ask me any question, as well as let me know whether my screen as well as whether my voice is audible to you or not. So Devras, let me know, is my screen as well as my voice, is it audible to you? So is it fine if I start the session? Is it okay now? The screen is visible, right? It should be visible. I can see my screen. Okay, so if so, let us start our first live section for this course, which is quantum transport. So now, if you recall one of the fundamental relation between the conductance as well as the dimension of a device. So if you take a two-dimensional semiconductor and if you measure the what is the conductance according to its dimension, you can recall that the conductance G, it is given by sigma omega by L. So sigma here, it's a material property which is independent of the dimension of the device. And omega, it is the area of the conductor. And L, it is the length of the conductor. So these are this relation we already know. Now the question becomes, what will happen if we reduce the dimension of the device, and up to what limit we can reduce the dimension so that it can follow the Ohm's law that we have seen in the classical transport. So this is where the quantum transport comes into the picture. Like if you reduce the dimension, then the classical behavior is no longer valid. So we will see the quantum behavior of the charged particles. So so quantum transport, by the name, you can easily guess it's nothing but to study the motion of the charge carrier by treating the electron as a quantum particle. So instead of a particle behavior, we see the wave behavior of the charge carrier. Okay, so in classical transport, if you recall, if you are considering the device, the charge carrier is following the classical trajectory, then we are treating the charge carrier as a particle, and we are treating this as a charge as a particle, and it follows the Ohm's law that we have seen before. But we have to keep in mind that this Ohm's law is only valid when the device dimension is much larger than certain characteristics length. So, like device dimension, let's say it is L, then it should be greater than de Broglie wavelength or the mean pre-path or the phase relaxation length. So this is only if this condition is satisfied, then we'll see the Ohm's law, and the charge carrier behaves like a classical particle. Now, when we look at the quantum regime, we are treating the charge carrier as wave, and this classical behavior is no longer valid. We can't apply the Ohm's law that we have seen in the classical transport. And this quantum behavior we typically see when there are two conditions to it. Like if you reduce the temperature of the system, then it's possible to see the quantum transport. And another way to see the quantum transport is by reducing the dimension of this device. So these are the two possible ways. So for this course, what we are interested in, we are more interested in studying the quantum transport in the mesoscopic range. So if you recall, there are two range according to the dimension of the device. There are microscopic, mesoscopic, and microscopic. So mesoscopic range, it's the range where the dimension is it's larger than the atomic dimension, but it is not large enough to satisfy the Ohm's law. So this is in between this macroscopic and microscopic range. So this course typically focus on this mesoscopic range. So to see what are the effect of a quantum transport, what we can take the example of MOSFET. So MOSFET, these are nothing but these are fundamental building block of processor, and this is nothing but a switch. This is off state, and it also have on state. So depending on the gate voltage, we can change the behavior of MOSFET either to a switch, open switch, or a closed switch. So what will happen? So over a year of 60 years, we have seen the dimension of this MOSFET getting reduced from 10 micrometer to a dimension of 14 nanometer. So, so for 10 micrometer, if you see the IV characteristics, what we have seen. So if you plot the gate voltage versus the drain current, then typically it shows when you increase the gate voltage, then the current increases linearly. Then after a certain gate voltage, it reaches a saturation value. So this is the IV ideal IV characteristics curve. Now, when we reduce the dimension, what will happen to this IV curve? So for this, when we reduce the barrier width, so typically we are reducing the distance between the source and the drain. So what will happen? The potential barrier, which was a step function earlier, it's a well-defined step function earlier. Now, because of this size reduction by changing either the oxide thickness or by changing the distance between the source and the drain, what will happen? This there is no longer a well-defined potential barrier. So it becomes a profile like this. When we apply the voltage, there is no longer a well-defined barrier. So because of this, what will happen? Instead of a zero current, so when we don't apply a gate voltage, there is ideally there shouldn't be any drain current. But because of this size reduction, what will happen? There will be a leaky path. So instead of a zero drain current, we'll see a leaky drain current because of this size reduction. So this is the effect due to this is the size reduction effect. So this leads to a non-zero leaky current when we reduce the size barrier, and this is also known as the third channel effect. So to suppress this short channel effect, what the modern transition transistor, they should follow a natural length. So they must satisfy natural length to suppress this short channel effect. So that is lambda, it should be equal to epsilon si tsi tox epsilon ox. This you can also write as a channel. So epsilon, this is the permittivity of the channel and this is the permittivity of the oxide layer. T is the thickness of the silicon layer and TOX is the thickness of the oxide layer. So this is the scaling limit. So this is nothing but this is the physical boundary. And if you reduce the dimension of the transistor beyond this physical boundary, what will happen? There will be short channel effects because of the size reduction, and because of this we'll see a leaky current, as well as we'll see the effect due to the quantum tunneling, as well as some of the effect related to the loss of electrostatic control. Okay, so they should modern transistor they should satisfy this natural length. This is the scaling limit. Now, these are one of the issue that we have seen because of the size reduction. So another issue is, so one is we have seen is the leaky current, and another is the uniformity of the device performance. So because of this size reduction, if you recall, there will be a change in doping, the doping charge carriers, they are non-uniformly distributed, and because of this, there will be no well-defined doping profile, and because of this, we'll see, so the performance of this device, they fluctuate from one device to the another device. So these are two of these classical issues that we will see if you reduce the device length. Other issue is these the quantum issues that we'll see. One is the tunneling. So when we reduce the thickness or either the channel or the gate oxide, what will happen? The charge carrier will, instead of a well confinement, the charge carrier will now tunnel to the forbidden region. So T tunneling, it is approximately 8 per minus 2. This is one of the issue, and another issue that you will see is the gate induced charge carrier injection to the channel. This we'll see in details in our upcoming live session. Now the third issue, it is due to the quantization of the energy because of this size reduction. So this we can easily understand by, if you let us take one of the most commonly used example. It's the infinite potential well. So if you consider that the charge carrier, they are confined inside this infinite potential well, then by solving the Schrodinger equation, as well as by putting the boundary condition at x equal to 0 and x equal to a, you can easily see the wave function. There will be relation of wave function. This is nothing but root over 2 by a sine knx. This is kn is n pi by a for 1D case. We are considering the 1D case. So this is a length. And the energy, it is, this n here is nothing but the quantum number, and we typically in quantum mechanics we say it is the principal quantum number. And energy En, it is given by h squared square k square by 2m s squared, or if you put the relation of k, this is n pi by e So n square, I think this is not there. Okay, so this is so En, it is directly proportional to the n square. So instead of a continuous energy level, now we'll have a discrete energy level, which has a relation like this. So instead of a IV characteristics that we have seen earlier like this, now we'll have a stepwise IV characteristics because of this discretization of energy level because of the size reduction. So these are some of the issue because of the when we reduce the device dimension. One is the two of the classical issue. There will be leaky current, as well as uniformity will won't be there, and the quantum issue is one of these tunneling, and second one is the hot carrier injection that we'll see also, and the third one is the quantization of this energy level. Uh, Other kind of two of these example of transport we have seen in the lecture is one is the correlated transport and one is the uncorrelated transport. So uncorrelated is like a noisy system, and we are not that much interested in this uncorrelated system. What is interesting is the correlated system. So this is where we are able to suppress the noise that will be created in the system, or there will be able to see the bunching or anti-bunching effect. Okay. So to understand the behavior of the charge in the presence of a external magnetic field, if we recall classically, we mostly the first theory, the first model we considered is the Druce model. So this is one of the first model that is considered to study the behavior of the charge transport. This is nothing but a free electron model, and it assumes that the electron, the charge carriers, they follows the Maxwell-Boltzmann statistics, and also they are the so they behaves like a molecule of ideal gas. And for this, they also follow the relation, which is the Ohm's law. J is sigma E. This is the current density, this is conductivity, and this is the applied electric field. And these are a few of these relation that we have seen also. Conductivity, it is related to the relaxation time as n e square tau by m. Or you can also write the J as n e v d in terms of the Drude's velocity. Drip velocity. But the main problem with this Drude model, first one, if you recall, it doesn't consider the electron as a fermions. So electrons are fermions, so they should follow the Fermi-Dirac statistics. So the statistics that it is considered is the Maxwell-Boltzmann statistics. So this is not applied everywhere. So we have to consider the Fermi-Dirac statistics. Okay. And the second thing it doesn't consider is it completely ignore the presence of a contact interface. So So because of this, what will happen? We are typically ignoring the effect of a contact interface for the transport behavior. So when we merge two material, what will happen? They have different formulable. So because of this, there will be a non-zero barrier resistance. And because of this non-zero barrier resistance, these IV characteristics will change. So we have to consider the presence of contact interface to study what will happen to the transport behavior. Okay. So these are the two that the Roots model completely ignored. And third thing is the density of states. So when the charge carrier move from one side to the another side, let's say from source to drain, then they should have empty states or field states so that the charge carriers can move within this channel. Okay, so density of state, it's nothing but the number of states that are available in a range delta E. So for charge carriers to move from one side to another side, there should be states empty in the channel so that the charge carrier that is coming from source can occupy the one of the state of the channel. Also, when electron go from channel to drain, there should be energy state should be available there in the drain side. Okay. Uh, this is the density of state, and the third thing is the third thing. Oh, sorry, fourth thing is quite related to the Fermi-Dirac statistics. So this is the occupation probability. So electron should have a finite probability to occupy a state. So if there is no probability, that means the charge carrier cannot go to that state. So these are the fourth thing that the Roots model ignore to study the transport behavior. And we'll see a few mathematical relation how we can derive the density of states and the occupation probability of a charge carrier. So we'll not go through in the details. I will just write down the important relation that will help you to solve the assignment. Okay, so the main model that is used to find out the density of state, it is by considering these are confined inside a infinite potential well. So as we have seen before, for infinite potential well, you can write En as h cut square k square by 2m. Sometimes m you can write it as m star. This is nothing but the effective mass. This we will also see. K here is nothing but n pi by A or n pi by Li. So to calculate the density of state, we have to find out what is the volume occupied by one of the quantum state and what is the total volume of this the whole uh, what would I say? So whatever we are considering, so we are considering the potential well. So we need to find out what is the total volume of this potential well and what is the volume occupied a quantum state. And if we divide it, then we'll get the states, the total number of state or the density of states of this charge carriers. So for this, we found that for total number of states inside a if we recall, it is nothing but 4 by 3 pi q and the volume of one of the quantum state is pi by Lq. So total number of state from this let me write out the final expression. So kf, if you recall for the 3D case, it is 3 pi square number density to the power 1 by 3. This is for the 3D case. So density of state, this this is the general formula for finding out the density of states. So if you know total number of state and if you take the derivative with respect to the energy, then we can find out what is the density of state. And for 3D, by putting the K formula and by putting the N here, we found out that for 3D case, density of state is given by or m star h cubed power 3 by 2 square root e. So for 3D, the density of state is directly proportional to square root of e. And for 2D, if you recall, it remains constant. It is independent of temperature, sorry, energy. And for 1D case, it is inversely proportional to square root of e. And for 0D case, this is a delta function. Please always remember this fundamental relation. So those who have joined later in this live session, uh, feel free to ask me any doubt if you have while when I am going through the concept. If you have any doubt, feel free to ask me. Or when I am solving the problems, if you have any doubt or if you are getting another answer, let me know. Okay, so now another thing that the Druce model doesn't consider is the occupation probability. And electrons, typically these are the fermions, so they follow the Fermi-Dirac statistics. So the probability, the occupation probability that a electron can be found in a state of energy E, these are given by F of E. So this is the Fermi-Dirac statistics of probability of finding an electron in a state of energy E. So this is given by 1 by 1 plus e to power E minus EF by kBT. So EF here is the Fermi energy. So this is nothing but, so if you look at the overall formula, so it will be the energy at which uh, Fermi Dirac, the probability is 1 at temperature 0K. If you draw it, this somewhat looks like this. For 0K, the Fermi Dirac statistics is like this. So it is completely filled for energy less than the Fermi energy. Now, when we increase the temperature, what will happen? Those states that are closer to the Fermi energy, they will try to move to the next energy level. So this becomes empty or this become, the charge carrier comes from here to here. You can't hear me. Uh, so, are you able to hear me from the start of the live section, or it is only this time you are not able to hear me? I think the mic is working from my side. Uh, are you able to hear me now? Let me disconnect my earphone. So, are you able to hear me now? Is it fine this time? I think it should be. Uh, can you please let me know whether I'm audible this time or not? Hi, Salom. Can you please let me know whether my voice is audible to you? So we are just looking at what is the Fermi Dirac statistics. So what is the probability that the electron will occupy a state or not? So we have seen. Still, I can't hear you. Um, Let me see whether there is a problem from my side. Give me 2 minutes. Can you please check whether it's a problem from your side? Or in the meanwhile, I will see whether I need to do anything or not. Everything is fine. No, my actually the screen that I have set for my iPad, the mic is off there, but for my laptop, its mic is on, so you should be able to hear it. If I turn it on from my iPad, there will be echo because there are two mics that is recording my voice. Let me see. Let me see. Let me see. Here you can easily listen. If I turn it on, then there will be echo. So, and from my laptop, mic is already on. Other than this slide, let me see whether. No, from my laptop, everything is okay. Speaker is on. Uh, Let me unmute you so that you can ask me. So I'm unmuting you. Hello, Mike. Can you speak now? What is the problem you're facing? It's like my laptop, it's able to, I can able to see that my mic is working. Um, so when we joined the session, you were able to able to hear my voice, or it's after some time it's
Now,
you are
now I
not.
can hear you, ma'am.
Oh, you can hear me. Okay, thank you for letting me know. Okay, so let us continue. We'll try to wrap it off the concept in 10 minutes, then we'll try to solve the problems. So we are basically we are looking at the Fermi Dirac statistics. So for and we have seen that for temperature 0 K, all the levels that is up to the Fermi energy, it's so the probability is 1. And when we increase the temperature, the charge carrier close to the Fermi energy level, they will occupy the states that is closer to this Fermi energy level. Okay, and the spread is about 4 kBT that contribute the transport of that contribute to the transport. We'll see one of the numerical problems related to this. And one of the useful relation that you should remember is for room temperature, the KBT, it is of the order of 25 MeV. So for me, energy levels. So this will in our upcoming live session, we'll see what are the importance of Fermi energy level. So it is like this is the level uh, within that and with close on the state that is closer to the Fermi energy level, they will contribute to the transport. So we are more interested is what is happening around this Fermi energy level. So that is why this is high importance. And if you want to define the Fermi energy level, it's nothing but the level for which all the states are occupied for temperature T equal to 0. Okay. So we'll see what are the other importance when we'll see compound semiconductor or the behavior of advanced devices. Okay. Now, so if the charge carrier, to consider what is happening to the charge carrier in the lower dimension, we need to see whether there are, so in the previous slide, we have seen whether there is available state in the lower band or the lower band or the band close to the Fermi energy level. So this is given by the Fermi Dirac statistics, and we need to see also whether there are any empty states in the system also not, so that they can flow easily from the source to drain, and whether there are available state from source and drain side. And the other thing is that it didn't consider is the importance of the contact interface. Okay. Basically, all electron filled up to the valence band level. Yes. So, this is how we define the Fermi energy level. Like the below the Fermi energy level, all the states are filled, and above it, all the states are empty. If you're considering the low temperature resin. Okay. But when we go to higher temperature, it's like some of the energy level below the in valence band, it become empty, and some of the states in the conduction band, they become filled. Ideally, the Fermi energy level, these are defined in reference to the T equal to 0 K. So this is the state, this is the energy level where all the states are filled for temperature T equal to 0 K, and above this level, all the states are empty. And besides that, these are some of the lacking of Drude's model. Like it doesn't consider the density of state, it doesn't consider what is the Fermi-Dirac state, is what whether there is a probability of, doesn't consider the probability of occupancy. Also, it completely ignore what is the effect of a channel interface. Sorry, the material interface, contact interface. So this becomes significant in the quantum regime. So that is why we are more stressing on density of state, Fermi-Dirac statistics, and the effect of contact interface. Because in quantum regime, this effect becomes significant. So we'll see in detail in our upcoming lab session. And also in the lecture, we have seen some of the definition related to the Fermi wavelength, lambda f. This is given by h by root over of 2 MEF. Mean free path. This is the distance between two collision. This is given by LM is VF tau m. And there are two types of mean free path. One is elastic mean free path where there is no energy exchange. And one of the example of the elastic mean free path is when we are considering the collision with the impurity atom. So this is the one of the example of elastic mean free path. Another type is inelastic mean free path where the energy exchange occurs, and this we typically see whenever the charge carrier they collide with the phonons, which are nothing but the lattice vibration if you recall, and the electron scattering. Okay, and also we have seen phase relaxation length. So L5 is VF tau phi. So this is the length beyond which the phase of this charge carrier get lost because of the scattering. So, and we have also seen the magnetic length LB, H cot by EB by half. As of now, just remember this relation. In upcoming lab session, we'll see what are the significance of this phase relaxation length and also the magnetic length. Okay. And we have also defined two types of transport regime. One is the diffusive and another is the ballistic. This is where the carriers travel randomly, and this is defined when the device dimension, which is the L, it is much greater than the elastic mean free path as well as the Fermi wavelength. And L is also, it is greater than L5, and L is much greater than LE, lambda F. This is the classical one, and this is the quantum one. So this we have seen in the lecture. So I'm just going through it in brief so that you can recall the definition before going to the solving the problems. So ballistic, the Fermi wavelength, it is less than the device dimension, which is also less than the elastic mean free path, also the phase relaxation length. But in the quantum regime, lambda f, it is approximately in the order of the device dimension, and but the device dimension is less than LE, which is the elastic mean free path, and L5. So this is the concept. This is that we have seen in week one of the course, quantum transport. Now we'll solve the problems that is related to this concept. So what I will do, I will go through the questions and I will let you to solve the problem first. Just recall the relation of different parameter and recall the concept. If you are able to solve it, please let me know the answer. If not, I will go through the solution in details. Okay. So I will give you some time to solve it. Then I will show you the solution. So the first question, it is based on the Fermi Dirac statistics. Uh, Let me zoom it. So it's given if EF is the Fermi energy level and F of E is the Fermi Dirac distribution function. Yeah, it's given F of E1 is 0.95 and F of E2 is 0.05. Then you need to find out what is E2 minus E1 by KBT. There are four options. One, first is ln19, second is 2 ln19, third one is ln19 by 2, and fourth one is ln19 plus 2. Go through it and please try to solve it, um, and let me know the answer. Uh, yes, you have asked about whether the notes as well as the recorded session will be available or not. So it will be stayed with you. There will be a Google Drive link, a Google Sheet that will be shared with all of you so that you can revise, you can revisit the lecture. Whether if you are not able to attend it, then you can use the link to the YouTube link to see the session. Also, I will upload it in my Google Drive and I will share the drive link. Okay, so don't worry, it will be available. Will be you will have the will just wait for few days. I think maybe not today, but by Monday or Tuesday you will get the link. It will be said by the NPTEL team. I will just but please try to attend the live section because it's like it's not like a one it will be interactive session. So if you have any doubts during the lecture in any of the concept, or if you have any other doubt, then you will be able to free to ask me. Please try to attend it. So live session will be on Friday from same time from 6 to 8. Okay. So try to attend it, or if not, if you are not able to attend it, then there will be links to see the lecture, recorded lecture. Okay. And also, one thing I wanted to say is uh, like uh, just let me know. One thing I wanted to say is whether if you have a doubt in assignment problem, then there will be a deadline to fill the assignment, right? After that deadline only I will be able to solve the problem. But before the deadline, I won't be able to clarify your query because it's a assignment, right? So only after you have submitted the assignment, I will be able to uh, solve your query. Okay. So the assignment one was not given time to submit. Will it be considered? Assignment one, I think there is a time on, I think it's on 4th February, right? The first assignment, I think it's only a trial one, but that is named as assignment 0, not assignment 1. Let me see. So are you able to solve this problem? Mm, week 1. Yes, the deadline for assignment 1 is on Wednesday. It's on February 4th. So it will be considered. Okay, let us go through the problem now. So it is directly related to the Fermi-Dirac distribution. You just need to put E1 and E2 and need to find out what is E2 minus E1 by KBT. Okay, so if we recall f of E, it is given by 1 by 1 plus e to power E minus EF by KBT. And if you take the inverse, 1 by f of E is nothing but 1 plus e to power E minus EF by KBT. From this, we can get E minus EF by KBT. It is 1 minus f of E minus 1. So this is 1 minus f of E divided by f of E. Okay. Now we'll put E1 and E2. So e to power E2 minus EF by KBT. So this will be 1 minus f of E1 divided by f of E1. F of E1 it is given. It is 0.95. 0.95. Sorry, it is 1 minus f of E, right? 1 minus 0.95. So this is 1 by 19. This is the first relation. For the second one, this is for E1, right? E1. Now for E2, we can similarly write it was E2 minus EF by KBT. This is 1 minus f of E2 by f of E2. And f of E2 is given, it is 0.05. 0.05 and this is 0.05. So this will be 90. So we need to find out E2 minus E1 by KBT. So you just need to divide 2 by 1. So when we divide it, it will be e to power E2 minus EF by KBT, e to power E1 minus EF by KBT. This will be 19 square. So left hand side is e to power E1 minus E2 by KBT. This is 19 square. Now we can take the ln in both sides. This will give 2 ln 19. So that means E2 minus E1 by KBT. ln is 1. This is 1. This is 2 ln 19. So that means the question, the answer to this question is 2 ln 19. I think it's option B. Okay, now let us go to our second question. It's a bit conceptual one. So second question is elastic mean free path in doped semiconductor generally decreases with increasing the dopant concentration, or it is shorter in materials with lower N, or it is independent of carrier density, or the fourth is increases with temperature due to phonon effects. So what will be the correct statement to the elastic mean free path? Can you guess the correct answer? So if you recall the elastic mean free path, it is there will be no energy exchange. But if you recall the inelastic mean free path, there will be energy exchange. Okay, and elastic mean free path typically occurs whenever we are considering the scattering due to impurity. So dopants, whenever you are doping a conductor, sorry, you are doping a semiconductor. So it's like you are adding the impurity to this system. So when we say we are considering the elastic mean path, so it's like the scattering due to the doping ions. And when we consider the inelastic mean path, it is due to the phonon scattering, phonon or electron scattering. Okay, so it's given elastic mean path in doped semiconductor generally decreases with increasing dopamine concentration, that is higher end, which is true, because whenever you increase the dopamine concentration there will be more scattering, and the mean p path, which is the distance between two consecutive collision, they will decrease when we increase the dopamine concentration. So the answer to the question is already A. Let us see whether the other options are also correct to the elastic mean free path or not. B option is it's shorter in material with lower N, so which is not true. Whenever the dopant concentration is less, then the elastic mean free path increases. So it's like inversely proportional to the doping concentration. Whenever you increase it, then the elastic mean free path will decrease, and whenever you lower the doping concentration, it will increase. So it is not true. Third option is it is independent of carrier density, which is also not true. It depends on the carrier density. And the fourth option is it increases with temperature due to the phonon effect. So this is not possible, because if there is a phonon effect, there will be energy exchange. Then it's not a elastic mean free path, it's the inelastic mean free path. So that is why the correct answer to this problem is A. Okay. Now let us move to our third question. Third question is, it's a n-type silicon sample of 10 to power minus 3 length and 10 to power minus 10 meter square cross-sectional area. It has a impurity concentration of 5 into 10 to power 20 atoms per meter cube. So impurity concentration is given. It is 5 into 10 to power 20 atoms per meter cube. Length, it is 10 to the minus 3, and cross-sectional area is 10 to the minus 10. And it is also given the mobility of the charge carriers. It's a 0 point. Mobility is n types. Let's say it is n 0.125 meter square per second. Then what is the resistance of the sample? What is R? Given the carrier density, the length and the cross-sectional area as well as the mobility. Try to solve it and let me know the answer. Just quickly recall what is the relation between mobility and the resistance as well as the length and the carrier density. If you recall the formula, it's will be able to solve. Okay, let me see whether you are getting the correct answer or not. Scaling limit. So for this, we can consider it's following the Ohm's law. So according to the Ohm's law, what will be the resistance of this sample? You can easily see the device length is in the order of 10 to the minus 3. So it's not in the quantum regime. So you can easily use the Ohm's law. Related to first question in assignment. First question means you are asking, no. So you are asking me the first question of NPTEL assignment. Um, the thing is, the deadline is on 4th February, right? So it's not good for me to like, if you have any doubt, feel free. There will be a Google group, right? So you can ask the doubts there. If you have any, like, whether you are finding that there is an issue with the assignment or anything like that. But because the deadline is not over yet, so I won't be able to solve the first answer to the assignment one. Okay. So it's a conceptual one. I can see that its scaling limit or MOSFET can be improved. Right? So you just need to go through all of this and also try to revisit the lecture content. Also, I have also explained it in this live session. Okay, how this scaling limit is affected. Just revisit the slides and weekly contact, or uh, you can also see my, like, it's not possible for me to answer it directly because it's a conceptual one. Just try to revisit the lecture content. It's a direct question, so you will be able to answer it. Okay, so for now, for our problem, so if you recall, R is rho L by A, right? This you already know. And L and A, these are already given. Length and area is already given. Rho, we need to find out the resistivity. Rho, if you recall, it's the inverse of conductivity, which is 1 by sigma by A. And so our first job is to find out what is the conductivity, sigma. So sigma is nothing but, so this is the end-doped semiconductor, right? So it says single carrier. So if you recall the semiconductor physics, we typically write sigma as Ne mu n plus Pe mu P whenever you have both hole and electron. But when you have single type, we can consider only this. So this is end-doped. So sigma is Ne mu n. N is also given the number density. It's 5 into 10 to the power 20. E is given 1.6 into 10 to the minus 19, and mobility is 0.125. Do check the units while doing the calculation. If the units is not matching, try to convert the unit. Okay. For this, the units are in, they are in proper unit, so we don't need to change it. And if you calculate it, this will come as 10. So conductivity is 10. So R is 1 by 10. L is given 10 to the minus 3. And area is 10 to the power minus 10. So this will be 10 to the 6 ohm. So which is nothing but 1 mega ohm. This is the resistance of this end-doped semiconductor. Answer B. Okay, so let us go to our next question. This is also related to the third question. So instead of n dope, now we have a germanium semiconductor which is doped with accepted impurity concentration of P is 10 to the power 15 atoms per centimeter cube. For the given hole mobility, mu P is given, it is 1800. The resistivity of the material is, what is the resistivity, which is rho? Can you calculate it? Okay, so let me quickly solve it. So sigma, sorry, rho, it is nothing but 1 by sigma. Sigma is, this is the whole, for this is whole P E mu P. P is given 10 to the power 15, E is 1.6 into 10 to the minus 19. Mu P is 1800. So this will give 0. 3.472 ohm centimeter. Option C. Fifth question, it's related to Moore's law. So it is, so we need to find out which is correctly related to Moore's law. One is option A is whether the speed of the operation of, it is related to the speed of operation of bipolar devices, or it is related to speed of operation of MOS devices, or it is related to the power rating of the MOS devices, or it is related to the level of integration of MOS devices. Which one of the following you seem it is related to the Moore's law? The correct option is option D. Okay. So it's related to the level of integration, like the compactness of the MOS devices. So the statement is that like the number of transistor increases because roughly double every 2 years because of the invention of the integrated circuit. So it is quietly related to the level of integration because the transistor is getting double. So level of integration is getting increased. So of answer would be option D. It's not related to speed or the power rating. Okay. Question 6 is quite easy. It's given the occupancy probability according to the Fermi-Dirac statistics is given P of is 1 by 1 plus e to power e minus ef by kbt. Find the probability of occupancy of a quantum state, which energy is 0.05 electron volt above the Fermi energy. You can assume a sample temperature of 450 Kelvin, and we can take the Boltzmann constant as 1.38 into 10 to the minus 23. And it's also given E minus EF is 0.05. So you just need to put all this information into this relation and find out which one of this option is correctly giving the answer to this problem. So let me just solve it. So KBT, it is 1 by 1.38 into 10 to the minus 23. Temperature is given 450. This will be, and you can also divide it by 1.6 into 10 to the minus 19, so that you can get the energy in terms of electron volt. This will come out as 0.0388. That means P of P is 1 by 1 plus e to power 0.05, 0.0388. This is will be 0.216, which is option B. Question 7. It's given consider two devices with the same epsilon Si, epsilon Ox, and Tox. So epsilon is the permittivity, T is the thickness. But they have different silicon body thickness. Device A is, so there are two devices. One is A, one is B. They have same epsilon. Permittivity is same. Oxide thickness is also same. Sorry, oxide permittivity. Thickness of oxide is also same, but it has different thickness of silicon body. And it's given TSIA, sorry, TSIB is equal to 2 times of TSIA. Then you need to find out which of the following is true for the scaling limit. Whether the scaling limit is same for both of the devices, or lambda b is 2 times of lambda a, or lambda b is half of lambda a, or lambda b is root 2 times of lambda a. Which of this is true for this case? Recall the scaling limit formula, use it, and let me know the answer. It's directly related to the scaling limit formula. Option C. Okay, let me go through the solution first. So lambda, it is related to the epsilon Si. Si, we are considering this is the channel. Channel is made up of silicon. So that means it is epsilon Si Tsi Tox divided by epsilon Ox. So this is the scaling limit. It is directly proportional to the product of square root of product of thickness, and also directly proportional to the F's permittivity of the channel. But it is inversely proportional to the square root of epsilon permittivity of the oxide. So according to the condition given here, these are all same, only the thickness of the silicon body is different. So lambda is TSI. So it is directly proportional to root over of TSI. So that means lambda B by lambda A TSIB root 2 TSI, and it's given SIB is 2 times of TSI. So lambda B is root 2 times of lambda A. Scaling limit of the device B is root 2 times of the scaling limit of A. Let me know whether you have any query in between. Okay, I will try to clarify it as much as I can. If not, I will also let you know the answer in the next live session. For this, it is option D. This is the relation that you need to consider and you need to remember. Okay. Question is quite straightforward. It's a 3D free electron has Fermi energy EF. By what factor does the density of state at energy 4EF exceeds that at EF? So we need to we need to compare the density of states for energy E equal to 4EF and density of states at energy E equal to EF. How they are related? Whether they are equal or whether this is twice of the first one or it is 4 times of the first one or it is 16 times of the first one. Which one of these you think is the correct answer to this? Remember, it's given 3D free electron. Then density of states changes when you are considering different dimension. For 3D, it is different. For 2D, it's quite different. For 3D, what do you think the density of state? What is the dependency of density of states on energy? It is square root of A, right? For 3D case. For 2D, it is a constant. For 1D, it is 1 by square root of A, and for 0D, it is a delta function. So DOS of equal to 4 if this should be, so that means this is 2 times of square root of EF, right? And density of states of E equal to EF would be that is proportional to square root of EF. That means this is twice of the density of state at energy E equal to EF. So the correct answer to this is option B. Just cross check the dimension and use the relation according to that. Okay, if you take another dimension, the question is asking about one dimension and you are considering another dimension, then we'll get wrong answer. So please be mindful when you are reading the question and solving the problem. Okay, question number 9. It's a conceptual one. It's asking silicon is not suitable for fabrication of light emitting diodes because it is a indirect band gap semiconductor, or it is because it's a direct band gap semiconductor, or it's a wide band gap semiconductor, or it's a narrow band gap semiconductor, or none of the above. So why we are not using silicon while fabricating the LEDs? What is the possible reason behind this? So for this, if you recall the semiconductor physics, so you have two types of material. One is the direct band gap semiconductor, one is the indirect band gap semiconductor. So direct band means, if I want to express it in picture, so it's like the conduction band, valence band minima. Let's say it is valence band and it's conduction band. They occur at the same point. This is the conduction band max minima and this is the valence band maxima, right? They occur at the same K value. So this is the EK diagram that I am showing. They occur the same value. So if it is the EK diagram is like this, so that means this is a direct band gap semiconductor. But you will see some of the materials instead of this, we'll see they have EK diagram like this. So this conduction band minima and the valence band maxima, they are separated in K space. One is, let's say, here and one is at, this is K1 point, this is K2 point. So this is for indirect band gap semiconductor. So what will happen? So whenever the electron make a transition from the highest state to the lowest state, what will happen? So for this to come to this valence band minima, so there will be a change in energy. Also, there will be a change in momentum. They should follow this rule. So because of this change in momentum, this because of this additional constraint, what will happen? Whatever energy is utilized for the change in momentum, it is lost for lattice vibration. So that is why whenever the charge carrier is making a transition from high state to the lowest state, the total energy of this high state, some part is getting lost because of the change in momentum, and some part it will emit in terms of light. So that is why we are not considering indirect band gap semiconductor for devising the LEDs. Okay, but if you see the direct band gap semiconductor, so whenever electron make a transition, whatever energy it has, it will completely release in terms of light. So there will be a fully utilization of energy to construct the LEDs. So that is why we uh, silicons are not used because it's a indirect band gap semiconductor and we are not using it for the LEDs. And for direct, if you want to uh, mm, check what are the direct band gap semiconductors, so gallium arsenide is one of the example of direct band gap semiconductor. These are typically used for making the LEDs. Answer would be option A. Okay. Now, the question number 10, it is related to the MOSFET. It's given for a N-channel E-MOSFET, given VTH. This is the threshold voltage. It is given 5 volt. What is the condition to turn on this device? Given the threshold voltage is 5 volt. What is the condition to turn on this device? And whether BDS should be greater than VDS means the voltage between drain to source should be greater than 5 volt, or the voltage between the gate and source it should be 5 volt, or the voltage between the gate and source should be less than 5 volt, or the gate voltage is equal to 5 volt. What is the condition required to turn on this MOSFET given VTS is 5 volt? Which one of the following you think is the correct one? Let me, it's better I think if I go through the plots. This is IDS. This is V threshold, VGS. This is the IV characteristics. Or we can also plot it in terms of the gate to source voltage. For different gate voltage, we'll get plots like this. So they typically have three reasons. One is the okay, let me plot this also here. This is so they have three reasons. One is the ohmic reason. This is where the this is the ohmic reason. This is the saturation reason. And this one is where current is low. This is the cutoff reason. Almost zero, current is not flowing. So ohmic reason, let us see the reason in details. Ohmic reason or the linear reason. So this is where the gate to source voltage is less than VTH. So that means the drain current is zero. So this is the case where MOSFET act like a open switch. Now for the ohmic reason, right? So this is what I mean. It is the cutoff reason. In cutoff reason, the gate to source voltage is less than the threshold voltage. That is why we are getting no drain current, and the MOSFET is acting like a open switch. For ohmic reason or the linear reason, this VGS is greater than VTH, and but the VDS it is less than VGS minus VTH. So you can see here the current is gradually increasing linearly. So that means the MOSFET is on state. For saturation reason, here also VGS it is greater than the threshold voltage, but VDS here is greater than VGS minus VTH. Here also the MOSFET is on. Current is flowing through this MOSFET. So that means the condition to turn on device that the VGS, it should be greater than the threshold voltage. So the answer would be option C. Question 11. There is a metallic island. It has a total capacitance of 0.5 attofarads. Calculate the charging energy EC and determine if Coulomb blockade is observable at room temperature T equal to 300 K. So there is a metallic island and its given capacitance C is 0.5 attofarad. Attofarad means 10 to the minus 18. Atto means 10 to the minus 18. So you need to find out what is the charging energy and you need to decide whether Coulomb blockade effect is observable at temperature T equal to 300 K. Can you recall what is the expression for the uh, charging energy? So EC, if you go through the slides, it is E square by 2C. C is given. E we already know it is 1.6 into 10 to the minus 19 by 2 times of 0.5 into 10 to the minus 18. This will be 2.56 into 10 to the minus 20 joule. In electron volt, what you have to do, just divide it by 1.6 into 10 to the minus 19. This will be 0.16 electron volt. This is the charging energy. Now we need to check whether the Coulomb blockade effect will be there or not at temperature T equal to 300 K. For that, we need to find out the thermal energy first and compare it to the charging energy. So thermal energy for temperature 300, it would be 1.38 10 to the minus 23 300 divided by 1.6 into 10 to the minus 19 so that I can calculate it in terms of electron volt. This will be KBT will come 0.026 electron volt. Here you can see the EC, it is 0.16 electron volt and KBT is 0.026 electron volt. That means the charging energy is greater than the thermal energy. So that means the Coulomb blockade effect will be observable because the charging energy is greater than the thermal energy. If it is the otherwise, like it is less than the KBT, then we won't see the Coulomb blockade effect. Okay. Question number 12. It's quite easier one. It says which of the following represent the density of states of a quantum dot system. Can you uh, let me know the answer? Which one of these following graph correctly represent the density of states of a quantum dot system? Yes, option D is the correct answer. So for quantum dot, it's a quasi 0D system. So we'll see the density of state behave like a Dirac delta function. This is for 2D. It is behaving like a, so it's like if you take quantum wire, 2D quantum wire. Sorry, this is 1D, right? C is for 1D. So you, if you take 1D quantum wire, you will see the effect. This is for 2D case, constant density of states, and this is for the 3D case where it is square root of E. Question number 13. It's given copper as electron density and is 8.5 into 10 to the power 28 per meter cube. What is the Fermi wave vector and Fermi wavelength assuming electron movement inside a 3D infinite potential well? You need to find out what is kf and what is lambda f, assuming the charge carrier is confined to a 3D. Or you can say it is confined inside a 3D Fermi sphere. What is for C? So C is for 1D case. It is inversely proportional to square root of E. Okay. And the example for this is quantum wire or nanorod, carbon nanotubes, if you say. If you recall the 3D case, there is a relation of kf is 3 pi square n to power 1 by 3. N is already given to us, so we can directly calculate what is the Fermi wave vector. I'm just directly writing the answer. Just check while you are calculating, just check you are getting the answer that is similar to me or not. Okay. So this is 3 pi square 8.5 into 10 to the power 28 to the power 1 by 3. So this will come around 1.36 into 10 to the power 10. Lambda f we can easily calculate because we know kf. So this is 2 pi by k. 4.6 10 to the minus 10. Or this will be 0.46 nanometer. Let us check. This is 1.36. So answer would be option A. Yes, you are correct. Answer would be option A. Okay, question number 14. It's related to diffusive or ballistic transport. It's given an experimental measurement of a 2D electron gas at 4.2 Kelvin. It shows a mobility mu of 10 to power 6, 10 to power 6, and the effective mass, it is 0.067 ME. Carrier concentration is 10 to power 12 per centimeter square. Calculate the mean free path and determine if it is ballistic or diffusive for a device length of 5 micrometer. First, you need to calculate what is the mean free path. Then you need to calculate what is the whether it is possible to see diffusive or ballistic transport for this case. And be careful that it's a 2D case, not a 3D case. So according to that, you need to use the relation. Let me solve it. I think it's better if I solve it. So for 2D case, we have seen the relation of 3D case, right? We have calculated what will be the kf, what will be the lambda f for the 3D case. But for 2D case, let us calculate what will be the kf and lambda f. So for 2D system, we can take kx is nx pi by lx and ky is ny pi by ly. So that means the k space volume for a single state this would be v single state. This is pi by lx pi by l1 pi square by v. V is lx into ly, or I think it's better if I write it as a pi square by a. Now the total volume of the k space would be k space volume. It would be in 2D, we'll consider in 3D, we are considering a sphere, and we are taking states up to the cave. But in 2D, this sphere we can take it as a circle. So the k space volume, total k space volume is pi k square. Or to be exact, pi kf square. So that means the number of states, number of filled state in k space, it would be n is v, what is the total volume divided by sorry, I'm writing it is volume, it should be area of single state multiplied by 2 for the spin state of these electrons, and half is because we are considering while calculating we are considering both plus or minus 1, so there will be reductancy, so that is why we are taking half, only we are considering the plus half state. This will, if you simplify it, just put this one and v state here, you will get this is pi k square, pi square by a, this is half. So we need to find out kf, right? So kf square, it is 2 pi n by a. N by a is this is the density, carrier density. So for 2D case, we have kf as 2 pi n to power half. So that means we know the kf. Now we can easily find out what is the mean free path, right? So mean free path, if we recall, it is lambda m is Vf tau. So to calculate it, you need to first find out what is Vf, the Fermi velocity. Then you need to calculate what is tau. From that, you can calculate what is Lm. Okay. So as I have already given what is cave, I want you to calculate what will be the LM and what will be the whether the transport is ballistic or whether it will be diffusing. So I will discuss. Uh, I'm giving you as a homework problem. So just write down the question and let me know the answer in the next live session. Okay. For now, let me ask whether you have any doubt for the problems that I have solved for today. Let me clarify it, or I will stop for today because it's almost time. Just use this cave formula 2 pi n to power half. Find out what will be VF and what will be the tau. From that, you can calculate mean free path. And to check whether it will be diffusive or ballistic, you need to go to the definition of ballistic and the diffusive transport. What is the condition required? Just check the condition whether it is satisfying or not. If it is satisfying, then it will follow that transport. Problems for now, just note down this problem. Just solve it when you get the time. Other problems that will be shared with you. Okay, don't worry. All this problem, all the slides, all the notes that I'm making during the live session, that will be shared with you, as well as I have also recorded this video, so you will get the link to the video. Okay, and that sheet it will be shared by the NPTEL team. Just wait for a few more days so that I can also upload. Also, the NPTEL team can share it with you. Okay. Yes, you will get the live session link. It will be shared with. It will be shared. Okay. I think it will take some time, but just wait for a few days because I need to upload it. I will need to share the link. Then they will share the sheet link. Okay. Any other doubt you have? We want previous assignment. What do you mean by previous assignment? It's the first live session, right? So this is the first we are doing this numerical problems. Are you referring to the NPTEL? The quantum transport has been from 3 years. Okay, so that I don't have any access to it. The assignment that has been floated in previous semester, so I don't have any access to it, so I won't be able to share it. How to get them? So one thing you can do if you want to uh, uh, see the question that has been asked, you can just write down your query in the Google group. Okay, just ask the NPTEL team if they can share the assignment, but I don't think you will get the link. But you can try to uh, write down your query in the Google group. They will reply you. They will let you know whether they will share or not. Any other query? Okay, so if you have done, if it's okay from my side, then Thank you for joining the session. I hope the problems that I've solved will be helpful for you to solve the problems of assignment. We'll meet on next week, same time, Friday on 6 to 8 to solve few more problems that is related to the concept of week 2. Please try to join the session and clarify your doubts by asking me during this live session. Okay. For now, let me end the session. Thank you for joining. Goodbye, everyone.